Thanks for watching. I have nothing to disclose. So real-time MRI has proven to be a powerful tool to understand articulators during speech production. Here's an example showing a mid-sagittal view. But trade-offs always exist between the spatial and temporal resolution, SNR, and potential distortion due to the undersampling. For years, 2D real-time MRI has been well established for speech applications to enable visualization of dynamic vocal tract shaping. However, if we want to have a full understanding of the complexity of the vocal tract, information is limited in 2D. To address this, 3D real-time MRI has been recently developed to visualize the entire vocal tract shaping. And here's an example showing the uniqueness of this technique, which is the first to image tongue set channeling and tongue grooving in axial and coronal views, while articulating English sound L and S. However, the spatial and temporal resolution has to be compromised if we push to the 3D, so the question is raised, can we improve that? Our motivation comes from the current imaging protocol of the 3D real-time MRI. Let's take a close look of this data acquisition. It uses the stack of spiral GRE results. In the KZ versus TR plots, it uses the linear order along the KZ, which is fully sampled. Through this wheel on the left, it changed the golden angle per 12 TRs in the KXY plane, which is identical sampling along each KZ per time. We believe there exists some redundancy through acquisition, so how can we improve the sampling efficiency through 4 dimensions? Our goal is to improve the spatial and temporal resolution of the 3D real-time MRI through innovative data sampling. 4 sampling schemes are proposed here. Case 1 is the current protocol I illustrated before. Here each dot represents single spiral arms in the KXY plane, and its color represents the initial angle. Case 2 applies the golden angle rotating in the KXY plane per each TR, which is represented here by the color of the dots changing per time. Case 3 keeps this feature while changing the order of the KZ to the bit reversed order. And Case 4 utilizes the variable density randomized order in the KZ direction, as well as using the golden angle rotating in the KXY plane. We use constraint reconstruction combined with the spatial total variation term, as well as the temporal finite difference terms as regulations. Here's an example of the parameter sweeping. Now first check out the upper left corner. This is the result with trivial regulations. See how noisy in the mid-sagittal, and we cannot differentiate the articulator boundaries in the intensity versus time plots. Now looking downwards, as the spatial term increases, we observe the denoising effect in the intermediate and then spatial blurring. Now let's compare horizontally as the temporal term is increased. We again see the deblurring in the middle column, and then it turns out to be the motion blurring in the extreme case. Now we applied a similar strategy at the finer scale. A suitable parameter set was chosen and applied to all other proposed sampling cases. Our next step is to find the best case among the 4. To allow pairwise comparison, we choose 4 temporal cuts from 3 views, mainly focusing on the movement for the lips and tongue. For the first 2 cases, it compares the effects of the golden angle rotating change per TR. Let's take a look at the mid-sagittal plane. Case 2 captures the sharper features around the oral cavity, and in the intensity versus time plots, the small dots in the case 2 as well as the cavity pattern shown in the second plot reflecting the lips fluctuations as well as the tongue root movements. They cannot be detected in the case 1. Thus, we definitely think case 2 performs better. In the second 2 cases, the change happens to the order of the KZ. Again, a better depiction of the motion pattern can be observed in the temporal plots in both mid-sagittal and coronal views. Let's check the last 2 cases. The change happens in the bit reverse order versus variable density randomized order along the KZ. Please take a closer look at these results. You may be surprised by the substantial improvements in the last case. The clean background as well as the clear delineation of the motion patterns are evident in the time plots. Again, the fast leaps and tongue movement are well captured in the variable density case. Therefore, we definitely select the last case as our proposed method while keeping the case 1 as the original. The variable density trajectory allows us to flexibly choose the temporal resolution. Here are the results. On the right-hand side, when we move downwards, when the temporal resolution becomes finer, it can better capture the fast movement of the leaps, whereas on the left, when looking upwards, when the temporal resolution is compromised, we observe the higher SNR as well as deblurring effects in the mid-sagittal. The results illustrate a trade-off between the spatial and temporal resolution. Our next part focuses on the speech application of the variable density case. Two sets of the stimuli are designed. The first table shown here illustrates alternating low and high tongue postures for vowels. The result shows a whole tongue movement cycle, which starts from the high tongue postures to the low and back to the high tongue postures. It starts from the narrowest opening at the top part of the tongue body to the narrowest opening at the pharyngeal walls. Comparing the original and proposed results, the proposed methods capture better motion patterns around the tongue surface boundaries. While comparing with the reference results, we believe they almost share the same information. Here are 3 static snapshot captures from the low and high tongue positions. Again, the motion blurring around the tongue boundaries is very obvious in the original method, while in the proposed method, the features are sharper and better visualized, which corresponds with the reference. The second experimental design focuses on the alveolar consonant segments. These are much faster than previous vowel stimuli, requiring the creation of a rapid tongue tip movement. We pick pita and pete as examples. So in pita, we see a rapid contact of the tongue lip at the alveolar range in the proposed method, but this movement couldn't be detected in the original. This is also confirmed in the extracted intensity versus time plot. In pete, the contact of the tongue tip is greater and lasts relatively longer, but still the results around the tongue tip area in the original method are quite blurry. In the rhotic flex group, we observed a significant sublingual cavity when the tongue tip retracts. We selected the corresponding ROI region and plotted the mean intensity values over the time. A shallow curve is seen in blue for the original method during the cavity formation, but the orange trajectory is sharper and greater in the proposed method, which matches closely with the gray reference. The last case shows 3 tilted axial slices in bottle. Clear dark channels at the sides of the tongue are detectable, representing the lateral airflow. We believe the proposed method is capable of capturing the complex tongue shaping geometries. To conclude it, we demonstrated improved 3D real-time MRI of the vocal tract using innovative KT data sampling. The improvements in the spatial temporal resolution allow better characterization of speech production during rapid linguistic motion, and we believe it will benefit speech science. Here are the grant supports, and thanks to the MREL and SPAN group at USC. Thanks.